contract systems easier and reusable. So let me just give a very quick recap of what contracts look like, where I can write a function, and I can say this is supposed to be the function that takes an even number to an odd numbers in the second line. Then when I run it with a bad argument, I would got the error message that is dynamically checked, where it says, well, 13 is violating the specification, the contract. And it is saying that, well, the user of the inc function is to be blamed. It it identifies the responsible party that is causing the problem. And this is a very straightforward and expressive approach to write lightweight specifications. This has been extended to many different language constructs, and also with many expressive contracts, such as trace contracts that can check the trace of a value, and even session types, which can check if the communication of a session has all behaved as according to the contract. Of course, people have also put a lot of research into how to make sure the contract system itself is correct. For example, Christos worked on correct blame and complete monitoring for identifying whether an error message is pointing to the problematic module. And Herman, Greenberg, they have put a lot of work into making sure the contract doesn't consume excessively many memories. And also, Dan Felty and Ravi Findler, they have also explored how to make sure the contract does not slow down your program exponentially because it is using dynamic checks. And in order to prove contract systems correct, we know that sometimes we need to add more annotations to the calculus itself in order to track certain information about the proofs. For example, for the error reporting, we may need to identify the owner of each value. For space efficiency, we may need to keep the original unoptimized version in order to know if we are doing right, if we are removing redundant checks. And in order to prove time complexity, we will know that we need to check how many operations we have used in order just to prove the complexity correct. And so our work is an attempt at making sure that you don't need to create a new calculus each time you want to prove a new domain-specific property. Instead, we want to make sure that you can just use one calculus and assemble the information you need, and then prove the properties individually. So let me try to give you a taste of how we achieve this and how this can be done through a parameterized calculus. So here we have the usual expressions, and expressions we use the notation B to stand for boundaries, where we can write assertions, and assertions are like contracts. We also have proxies that are used to wrap around Howard values, so we can insert dynamic checks to protect Howard functions. Now, the things at the top, this is called the annotations, where we can substitute actual things like contracts and contract checking status in order to recover the original contract systems. At the bottom is how we reduce these how the assertions and how we reduce the wrapped values. If we substitute concrete examples that is highlighted in blue, we can recover the original contract calculus. For example, if I started with contract checking status OK, and I'm checking a contract over a natural number with a list of predicates, then I know that I just need to check if the predicates, they all hold for the given number n, and update the checking status to either OK or error if there is a contract violation. Otherwise, if I'm checking a contract for a pair, then I just continue by destructing the pair contract and checking the first component and checking the second component individually. For how the functions, I just create a wrapper around the functions waiting for application. When the wrapped function is actually applied, I will first check that the argument is correct by using the domain contract. Then I run the function with the checked value, and eventually I checked the result of application using the range contract. Through this is a basic example of how we can we can model the behavior of how the contracts in our parameterized calculus. But since we have make the contract part highlighted in blue and the global register part highlighted in blue as the parameters, we can just be more abstract and allow the contract system designer to substitute whatever information they need in order to complete their proof. For example, a specific collection of annotations and registers, we call them an instance. And in order to prove the correct blame that is identified by Christos Dimoulas, we can instantiate it with annotations that will tell me who has the control over the value that is being checked, the ownership labels. In order to prove space efficiency and its correctness, like it's not dropping checks, we can instantiate it with not just a single contract, but a pair of contracts where the second copy of contract is the original unoptimized version of contract that may contain redundant checks like K3 and K4. By associating it with a pair of contracts together, we will know that if we have correctly removed redundant contracts, because we know in order to prove correct, we need to keep the original versions around so that we know we don't lose any checks. Or we can also augment the register with a counter counting how many primitive operations we have used in order to prove time complexity correct. For example, between the second and the third step, there has been a contract check. Therefore, we increment the primitive counter from 5 to 6. Now, this is showing how we can instantiate the parameterized calculus with different parameters to know if we are with different parameter to know what we can prove. But one last piece we need to use is to connect different proofs between different instances. And in order to achieve this, first, let me show you how we can rephrase a proof about a calculus as a homomorphism of transition systems. So on the left is an example reduction sequence that is illustrating what is being written down in the lower part of the slide, where I might have a reduction sequence that is applying a wrapped function to a value. Now, if I just view this operator semantics very abstractly as a transition system, then I can get the diagram at the left. And for the diagram on the right, this is a very simple transition system where it only has two states, OK and error. And it could only ever transit from OK to error, but not going back from error to OK. Now, let me identify the reduction steps that involves the B construct for assertions and the proxy construct for checking hierarchy contracts. And we know that only when there is an assertion being checked, only at that point the state could be changed. Therefore, we collect all non-B construct steps into a state. And we try to create a homomorphism mapping the transition system of operator semantics into the simple transition system at the right. As long as we know that there can be this homomorphism, we know that the register can never be set from error to OK. That is, our contract calculus will never mask errors. And this proof is done because we know that homomorphisms preserve the transition structure. And we also know that the transition system at the right is so simple that it's obviously correct. So now we have different instances that contains different informations about the proofs. For example, the counter for the primitive operations. And what we can do is we can use instance projection to remove unused component either in the register or in the annotations. But when there is an instance projection, there will also be, we proved that, there will also be a homomorphism connecting the unprojected transition system of the unprojected instance and the transition system of the projected instance. Since this is a homomorphism, and since we have removed the counter from the register, we've got the original transition system that is at the left of this diagram. And as long as we already got the transition system that doesn't contain the extra counter, we can reuse the proof H checking. So we know that the calculus augmented with the counter for tracking confirmatory operations will never set the state from error to OK. And we have reused the proof. This way, you can just always create as many annotations as you want, put them together, and then you can just reuse previous proofs. So this, we have formed a recipe for making proofs reusable and proofs, and so that proving new dimension-specific properties is easy. You can just organize your proof, organize the information you need into the register for global information, or into the annotations for local information. Then you can assemble all necessary information together into a composite instance. After proving the individual properties, you can just use instance projections to reuse your previous proofs. So this is our insight where you can just use transition systems and instance projections to build a modular proof of contract systems. Sorry. So thank you. This is our presentation. Yeah.
All right, if you have questions, that microphone or this microphone.
Yeah.
Hey, interesting presentation. So if I understood correctly, basically you provide a way to compose different things and then decompose them so you can use existing strategies for proving things, right? That's correct?
Yes.
So what I was wondering actually, so you have these abstraction and you talk about blame assignment and correctness for blame and things like that. So my question is, like, can you reuse some of the proofs for blame assignment for other contract systems as well because of your abstraction, or is that not something that you provide?
Right, right. So we do hope that we can reuse the proof once it has been proven and reformulated as a current way. Right, but for the very first time, we have to redo the proof using the strategy we presented here in order to reuse it. So, yeah, we do hope that we can reuse, but we haven't actually done we have done it for Christos Dimoulas' original blame assignment algorithms, but we have not done it for more because we are focusing on the space-efficient application.
Yeah, because I was also wondering, because blame assignment is typically something where you have to change a lot of the semantics to make it work. Like you have to change how the proxies are represented and things like that. So I'm wondering how much of it can be reused across different contract systems, but we can talk about that offline if you like.
Yeah, sure.
Any other questions? All right, I have one question. So.
Yes.
If I understand, your system lets me adjust the way I use or implement contracts. So I might, for example, even though the asymptotic space and time is fine, maybe the constant is too big when my server gets too loaded, and I want to turn off the contracts half the time. So would your approach let me prove that that's okay, like that I'm not messing up or introducing new errors by only sometimes running the contracts?
So I think that would be possible, but also you have to first identify a way to know when you are turning off contracts and whether that would affect any checking process. So currently, we have fixed the checking strategy, but what you are going to check is allowed to be just nothing, which would represent not checking anything. But then you will have to design an annotation such that it checks only the portion you care about. And there's no hint about when you can check and when you don't need to check, and you have to figure that out by yourselves.
Okay. Yeah. All right. All right. If there are no other questions.